This video is about Argand diagrams. Argand diagrams are ways of representing complex numbers visually. We're already familiar with the idea of using a number line to represent real numbers. But the number line that we're used to seeing, it only has space for those real numbers. So we have our natural numbers, we have our integers, we have our fractions and our decimals in between. We have our irrational numbers, we have everything that we've seen up to this point, but we don't have a spot to put in imaginary numbers or complex numbers. So in order to accommodate that, what we need to do is actually draw another axis. We're going to have an axis for real numbers, which is essentially our number line. And we're going to have another axis, and that's going to represent our imaginary numbers. It looks an awful lot like our coordinate geometry plane, our XY plane. But in this context, my horizontal axis is my real axis, and my vertical axis is my imaginary axis. And I can scale it in the same way that I would a regular XY plane. So on my real axis, I've got my real numbers. And on my imaginary axis, I've got the imaginary coefficients. So this position, for example, represents 1i, 2i, 3i, and so on. We don't write the I, though, on the axis, just the coefficient. And I can locate any complex number that I want on an Argand diagram. So here, for example, we have the complex number z1, and it's 3 plus 2i. So it's got a real component of 3, and an imaginary component of 2i, and the coefficient there is 2, obviously. I can write this as a point. So this point is the point 3, 2. So I can then plot that point on my Argand diagram. So out to 3 and up to 2 on the imaginary axis, and there is my z1 on my Argand diagram. I can also calculate the modulus of this complex number, conjugate of this complex number. And the conjugate of this complex number is 3 minus 2i. Don't forget, the conjugate is just achieved by changing the sign of the imaginary part. And so that point then would be 3 minus 2. So out of 3 down to minus 2. And there is z1 conjugate. Take a moment to think about how z1 and z1 conjugate are related geometrically on the diagram. I can say that z1 conjugate is the reflection of z1 in the real axis. I can also draw what's called a modulus on my Argand diagram, and a modulus is just the distance from the complex numbers point back to the origin. You can see in this diagram that the modulus of z1 and the modulus of z1 conjugate are actually the same. So the modulus is just the distance from the origin, and the notation for it is modulus z1. Now you might recognise this from a couple of different chapters. So for example, coordinate geometry, we know that this means distance or length, which makes sense. And from algebra, we also know that it means absolute value. So again, those two things are related. Really, it's just how far are you from 0. So in this case, we've got a formula. If we've got z, we want to find its modulus. We're going to find the square root of a squared plus b squared, where z is a plus bi. So for my z1 in this case, the modulus of z1 is going to be the square root of, well, the a in that case was 3, so that's 3 squared. And the b in that case was 2, so 2 squared. So the modulus of z1 is root 13. So that's the distance that z1 is from the origin. Now I can see visually that z1 conjugate is actually the same distance out. So I would expect that when I find its modulus, it'll be the same value. So let's see how that works out. So the modulus of z1 conjugate is just going to be, okay, my formula is the square root of a squared plus b squared. In the case of z1 conjugate, a is 3 and b is minus 2. And notice that I'm putting a bracket around each number that I'm substituting in to avoid issues with signs. That equals to root 13. So it's interesting to note that the modulus of Z1 will always equal to the modulus of Z1 conjugate. As we saw in the last example, more than one complex number can have the same modulus. So in this example, I'm going to look at Z2, and Z2 is 3 plus 4i. And I'm going to first of all write this as a point, 3, 4, and then I want to plot this point on my Argand diagram. So 3, 4 is out to 3 and up to 4. So it's there. There's Z2. So I'm going to begin here by just drawing in the modulus of Z2. And then we're going to calculate it, and then we're going to have a think about what other complex numbers would have the same modulus. So there's the modulus of Z2. Calculation, of course, is going to be modulus Z2 equals the square root of 3 squared plus 4 squared. And that comes out as 5. And now I'm going to have a look at my Argand diagram and see what other complex numbers would have that same modulus. Well, they would be the complex numbers that were also a distance of 5 from the origin. So I think probably we could agree that the value 5 on the imaginary axis will be one location, minus 5 on the real axis, minus 5 on the imaginary axis, and 5 on the real axis. But I can actually identify all of the points that, I'm after realising that I didn't draw my axes on the same scale, so that's going to make things tricky. I'm going to mark in those points for the moment, and then in a moment I want to draw my diagram again so that I can actually use my compass to illustrate something nicely. Anyway, for the moment, all of these points have the same modulus as Z2. Take a second to think about Z2, 3 plus 4i. Are there any other complex numbers that you think you could write down that would have the same modulus as this? So I could have, for example, minus 3 plus 4i. And minus 3 plus 4i is here. I could have minus 3 minus 4i, and that would be located here. And I could have 3 minus 4i, which you might recognise as the conjugate of Z2, and that is located here. And all of these have the same modulus. The modulus of all of these is 5. They're all a distance of 5 from the origin. Okay, so I have redrawn my Argand diagram again, and I've marked in the point Z2, and I'm just going to illustrate something using the compass about complex numbers with the same modulus as Z2. And just to point out the reason that I had my little moment a second ago with my earlier diagram, you'll see here that in this diagram I've spaced out, or I've scaled my axes in such a way that the scales are the same. So I've got a gap of 2, a gap of 2, a gap of 2, and then on the imaginary axis I have that also. That just means I'm going to be set up well to draw a circle in a moment. If I look back up here, I set this one up with a gap of 2, a gap of 2, a gap of 2, a gap of 3, 3, 3. Now there's nothing wrong with doing that when I'm drawing any plane, whether it's the Argand diagram or the XY plane. I can totally do that as long as I'm consistent on my horizontal axis, all the gaps are the same. And as long as I'm consistent on the imaginary axis and all its gaps are the same. But it doesn't lend itself well to drawing things with a compass. So if I want to use the compass, I need to make sure that all my scales are the same in both directions. So now I have got my Z2, and I'm going to put my compass point on the origin, and I'm going to put my pencil on Z2. And notice that with the compass, what I've effectively done is measured a radius of a circle. So if I draw a circle now, with the centre at the origin, then I'm going to essentially be identifying all the points that are a distance of 5 from the origin. So I'm going to do that now. And you can see that when I've done that, that actually all those points that I spoke about earlier are on that circumference. And in fact, there's other points also that I didn't mention before, such as, for example, 4 plus 3i, and minus 4 plus 3i, minus 4 minus 3i, and 4 minus 3i. And you can see how every one of these complex numbers has a modulus of 5. They're all located at a distance of 5 from the origin. Clearly there are many, many more complex numbers that fit the bill for this as well, but I've selected the ones that have nice real number coefficients. So I've stayed away from things like root 2 plus root 3i, for example. So what I'd like you to do now is take a complex number. We'll call it Z3, 1 plus 2i. I'd like you to draw an Argand diagram for it and use your compass to identify as many different points as you can that have the same modulus as Z3. Calculate Z3 also, and just note when you're doing it that, as in this example, the conjugate of your complex number is going to have the same modulus as the original complex number.